Coininitial vectors. Hello everyone. Today, we are going to dive into a specific area of vector algebra. As you progress in your studies, you'll notice that vectors aren't just random arrows. They are often categorized based on how they are positioned in space and how they relate to one another. One particular classification we need to master is known as coininitial vectors. Now, don't let the name intimidate you. It's a very straightforward concept. Understanding this is absolutely essential, as it serves as a fundamental building block when we move forward to study how we add vectors together and how we represent them accurately within a coordinate system. So, let's get started by breaking down what this term actually means. Understanding coininitial vectors. Now, before we dive into the specific definition of coininitial vectors, let's take a moment to refresh our memory on the basic structure of a vector itself. This is crucial because the entire concept relies on one specific part of the vector. As you know, a vector is represented visually as a directed line segment. This segment isn't just a simple line. It consists of two very distinct points that give the vector its direction. First, we have the initial point, which you can think of as the tail. This is the exact spot where the vector begins. Then, we have the terminal point, often called the head. This is where the vector ends, and it's always indicated by an arrow to show us which way we are pointing. So, with that foundation in place, let's look at the formal definition. We say that two or more vectors are coininitial if they share the exact same initial point. To put that in much simpler terms, if you have a group of different vectors and they all start from the very same location, they are classified as coininitial. It doesn't matter if they are pointing in completely different directions, and it doesn't matter if one is much longer than the other. As long as that starting point, the tail, is identical for all of them, they are coininitial. In the next slide, I'll show you a geometric way to visualize exactly what this looks like. Geometric representation. Now that we have established the definition of a vector's tail and head, let's move from the theory to a geometric representation to see this in action. Imagine we have a single, fixed point in space, which we will denote as point O. Now, let's draw several different vectors, all starting exactly from the same point O, but extending out towards different locations. Let's say towards points A, B, and C. By doing this, we create three distinct vectors: vector OA, vector OB, and vector OC. Take a close look at these three vectors. Even though they are pointing in different directions and likely have different lengths, notice that they all originate from that same starting point, point O, because they all share this exact same initial point. We can formally classify vector OA, vector OB, and vector OC as coininitial vectors. This visual pattern is exactly what we'll see applied in the next slide, with a real-world example involving light rays. Real-world example: a light source. Now, I know the geometric diagrams we just looked at in the previous slide might seem a bit abstract, so let's bring this concept into the real world to make it more intuitive. Imagine you are standing in a dark room, and there is a single light bulb hanging right in the center. Let's break this down step by step to see how it relates to our definition of coininitial vectors. First, let's identify our source. We will let the exact position of that light bulb be our initial point, which we'll label as point P. Next, think about the light rays themselves. As soon as you turn that bulb on, light travels in straight lines from the bulb to various objects scattered around the room, perhaps hitting a table, a chair, or even the wall. Now, let's translate these paths into the vector notation we've been studying. The path of light traveling from the bulb to the table can be represented as the vector P. To T, the path of light traveling from the bulb to the chair can be represented as the vector P to C, and finally, the path of light traveling from the bulb to the wall can be represented as the vector P to W. So, what is our conclusion here? Because every single one of these light rays originates from that same starting point, point P, we can officially classify the vectors P to T, P to C, and P to W as coininitial vectors. This perfectly illustrates what we discussed earlier. As long as that tail, or starting point, is the same, the vectors are coinitial, regardless of which direction the light is traveling. Now, before we move on, let's summarize the key takeaways to ensure we don't miss the essential properties. Key takeaways. First, the most important takeaway is the shared origin. As we discussed in the previous slides, the only strict requirement for vectors to be classified as coinitial is that they must share the exact same starting point, or what we call the initial point. Second, remember the independence of magnitude. This means that the length of the vectors does not matter. One vector could be very long and another very short. As long as they start at the same spot, they are still coinitial. Third, we have the independence of direction. Just like the light rays in our previous example, these vectors do not need to point in the same direction. They can spread out in any direction across the plane. Finally, let's look at the mathematical notation. If you see vector A and vector B, and both are written as starting from point O, meaning they both originate at point O, then you can confidently state that these vectors are coinitial. Now that we have seen the geometric representation and a practical example with the light source, let's summarize the essential points you need to remember. In the next slide, we will look at some common pitfalls to ensure you don't confuse this concept with other types of vectors. Common mistakes to avoid. First, be careful not to confuse coinitial with collinear vectors. While we've discussed how coinitial vectors can point in any direction, collinear vectors are much more restricted. They must lie along the same straight line or be parallel to it. Remember, just because two vectors start at the same point doesn't mean they are heading in the same direction. Second, do not mistake coinitial vectors for equal vectors. As we touched on in our key takeaways, for two vectors to be considered equal, they must be identical in both magnitude and direction. In contrast, coinitial vectors can have completely different lengths and point toward entirely different parts of the coordinate system. The only thing they must have in common is that initial point, or the tail. Finally, please do not assume there is a fixed or specific angle between these vectors. You might be tempted to think they must be perpendicular, but that isn't a requirement. The angle between two coinitial vectors is flexible. It can be anything from 0 degrees to 180 degrees. Now, before we wrap up today's lesson, I want to pause and address some common pitfalls. As we've seen throughout this presentation, the defining feature of coinitial vectors is simply their shared starting point. However, it is very easy to accidentally overlap this concept with other vector properties. Keep these distinctions in mind, and you'll have a much clearer grasp of vector relationships as we move forward into vector addition.